Hello everyone. In this video, I would like to introduce our new paper, the SimMatchV2, Semi-Supervised Learning with Graph Consistency. And here is the overall framework of our SimMatchV2. So basically, in this paper, we propose 4 different kinds of the consistency from the graph perspective, where the first one is the node-to-node consistency, which is not here, and the second one is the node-to-edge consistency, and third one is the edge-to-edge consistency, and the last one is the edge-to-node consistency. And I will explain all different consistency later on. And basically, in this work, we consider each sample as a node on the graph. So here's the setting. Given a graph with k nodes, we will have the node labels p here. So basically, for the labeled sample, we will use the ground truth, and for the unlabeled sample, we will use the model's prediction. And we will also have the corresponding representation z here. So because each sample will be treated as a node on the graph. So if we have the representation here, we can simply calculate the cosine similarity to construct the edge in between the nodes. And here's the formula. And the first one would be the node-to-node consistency. So this is basically exactly the similar with the fixed match, and we don't claim this is our contribution. But in this paper, we just provide a unified view about how to consider this problem from the graph perspective. So basically, by giving an unlabeled example, what we expected is that the model's prediction from the strongly augmented view should be consistent with the model's prediction with the weakly augmented view. And we also apply a threshold here, which means that the loss will only be applied on the samples that have a very high confidence. And the second one is the node-to-edge consistency. So basically, the purpose of the node-to-edge consistency is to construct an edge by using the representation from the strong node, and then use the edge as the weight to aggregate the node label from the graph. And we expected the aggregated node label can be consistent with the label from the weak nodes. And here we apply the cross-entropy loss. And the third one is the edge-to-edge consistency. So basically, what we expected here is that the edge constructed from the strong node should be consistent with the edge constructed from the weak node. And here we also apply a simple cross-entropy loss here. And the last one is the edge-to-node consistency. So basically, this is somewhat similar to the reverse operation to the node-to-edge consistency. So basically, what we expected here is that we use the weak node to aggregate the node information from the entire graph, and we expect the node label from the strong node to be consistent with the aggregated node label here. So basically here, given a unlabeled weak node, which has the representation and most prediction, and then we concatenated the unlabeled nodes with the graph, which is just like the batch, to get the uppercase z, and also the uppercase y here. And next, we will use the representation matrix Z to obtain the pairwise edge matrix A. So this pairwise edge matrix is just the affinity matrix in the graph. So here we just simply apply the label propagation to propagate the graph for the infinity times. And finally, we obtain the y infinity. And we will also apply a cross-entropy loss in between the strong node label and the propagated label. And finally, we will also have the feature normalization here. So basically, as we have shown that in the node-to-node consistency, the training objective is to minimize the prediction between the weakly and the strongly augmented view. So basically, there is a significant gap that exists with the feature norm of different augmented views, especially between the strong and the weak augmented view. And we can also see that from this equation, like the norm of this edge doesn't affect the prediction. So basically, minimizing the gaps between the feature norm is not necessary. So to address the issue, we simply apply the layer normalization on this edge. And here is the result on USB classical CV benchmark. We can see that we achieved the highest freedom rank and the lowest mean error rates. And here's the experimental result on ImageNets. Right, so we also got the SOTA performance. And that's all of it. Thank you.